So we are going to start. Does anybody have any questions before I go into my regular spiel on anything? You guys totally understand earthquakes?
Yeah.
Yes. Great. Awesome. She's got the door. All right, so we're going to go over some terminology really quick, and then I'll briefly go over what I think you should go on both sides of your 3x5 note card. First off, right, we want to define our different plate boundaries and what type of earthquakes we would expect to see at each boundary. This guy?
Subduction.
Yeah, so subduction, convergent, big earthquakes. Okay? This guy? Divergent, aka spreading center. Small earthquakes. Why are they small?
Shallow area.
Because they're shallow, it's warm and shallow. Right? And then this guy, transform, can be large. We've had some small ones. We can also generate some big ones. It depends on how much rock is actually touching. So our three plate boundary types, these generate our differential stress. Which produces earthquakes. Okay? The definition of an earthquake. Right? This is a natural phenomenon. Caused by violent shaking of the earth. This happens from, let's see, rocks being stressed, being, I just spelled being. Being, wow. Stressed, suddenly, and overcoming the elastic limit. AKA breaking. On an atomic scale, what happens that generates these waves in relation to this term elastic? You guys remember?
Ductile.
Ductile,
Or elastic.
elastic. What happens in elastic behavior? I don't have a hair tie.
Stretches.
It stretches, but when I release the stress, it returns to its original shape, right?
Rebound.
So we have a break right here, but the atomic bonds on either side of this break, these are elastic stretching. And when this breaks, those elastic bonds go back to its original shape, and that generates our earthquake waves. Okay? 4 words?
Break, rock, and displace.
Yeah. Break rock. And displacement. Super important, this displacement. That's moving rock past each other, right? Either vertically or horizontally. Okay? Now, if I were to draw a diagram, this is a humongous tree. That's gigantic. We'll do a gigantic rabbit. Okay, so this is the surface. This point where the earthquake actually starts to move, this is called our focus, or the hypocenter. If we bring that all the way to the surface, this is called the epicenter. And what's this guy called if it's actually displacing the rock?
Fault scarp.
Yeah, this is our fault scarp. And in order to get this, we need a magnitude 6 or greater, right, to get a big fault scarp. Beautiful. When an earthquake goes off, it generates specific types of waves, right? We've got our body waves, and we have our surface waves. Body waves include our P waves, these are compressional. What's an example of a compressional wave?
Yeah.
Sound, right? I'm generating vibrations in my chest, it's going through my vocal cords, compressing the air to your eardrums, which are vibrating and interpreting, and you're getting the sound in your head. It's kind of creepy when you think about it that way. These are the fastest, right? We'll do about 6 kilometers per second. And these can go through solid and liquid. So you travel through both. Then we have our S waves. These are shear. These are slower. About 3 to 5 kilometers per second. And these can only go through solid. And then our surface waves, we've got our Rayleigh waves. Right, these are the elliptical ones. And then we have our Love wave. Side to side. These are the side to side waves. And these travel about 2, maybe up to 5 kilometers per second. And these are the slowest. You need at least 3 stations. By stations, I mean seismograph stations. And you do the change in time between the P waves and the S waves to determine your distance. We call this triangulation. You won't have to find one on the exam, but just be familiar with these terms and how we actually find it. All right, in terms of our ideal, keep breaking the chalk, our ideal fault rupture sequence is this point or this point where the earthquake occurs. How many of you think the top? How many of you think the bottom? The top. So we have time, stress. As stress builds, right when we overcome all the stress, it basically drops down to 0. Right? We have our earthquake as this is dropping. This is our earthquake happening, right, as this is dropping. As soon as it hits the bottom, the ground stops shaking, all the stress is released, and then we start all over again. So ideally we'll have a pattern like that. True or false? Most earthquakes occur at plate boundaries? True. Yes. Very few do we have at not plate boundaries. That was a bad sentence. Give me an example of an earthquake that is not at a plate boundary. Or behind us. Both sides. Either way. Basin and range, right? Technically it's not a plate boundary, but we are having earthquakes there. What is the difference between an aftershock and a foreshock?
One comes before and one comes after the main earthquake.
Yeah, which one comes before?
The foreshock.
Okay, beautiful. This is before main earthquake. That can be days, right? Weeks, months, even years beforehand. And we've used it to attempt to predict earthquakes, but not so accurate. Right, because it can occur days, weeks, months, even years beforehand. All right, the aftershock, after the main event, it's usually 1 magnitude or more smaller than the main one. Right, so if you have a 7.6, it'll usually be a 6.6 or smaller. Going back to our seismic waves really quick, which one has the highest amplitude? Surface waves. Okay, beautiful. Wonderful. There are two ways to measure an earthquake, right? We usually go by either the magnitude, also known as the size, or the intensity, which is like the effect. One way to measure our earthquake, right? We got this guy Richter, the Richter scale. This measures the size, and it's based on the amplitude of the seismograph. Each magnitude increase, I'm just going to do mag, so that's each magnitude increase equals 10 times larger and 32 times more energy. So our boy Richter. What is wrong with Richter's scale, though? Why don't we like to use Richter's scale? Yeah.
It was hard to measure the definite magnitude of the amplitude.
Yeah, so it's hard to tell the difference between the peaks of our seismograph. So if you're trying to tell between a 2.4 and a 2.5, right, you might have a hard time telling the difference. So we came up with the moment magnitude as our second way to measure the size of an earthquake. The important things to know, right? We need to know the strength of our rock, right? The difference between something like a hard rock, like granite, or a soft rock, like sandstone, right? These have different strengths. You also need to multiply it by the area, right? And how do we determine the area? We determine the depth to the focus using the aftershocks. Right, so trying to think of an area. We're up here. We need to figure out how deep this is. So the aftershocks give us the depth. And we need the length. We need the width, the length, and the depth, plus the strength of the rock. And that gives us our moment magnitude. Ultimately, this you get the strain energy. Strain meaning the internal deformation of a body. Stress is the external force. Right, so I'm stressing this piece of chalk, and the chalk strains and breaks in response to my stress. So stressed right now. Breaking chalk. Straining it internally. Got a new piece of chalk. Good. Thank your lucky stars you're not a phone book, right? Way too much. I'm going to totally show my surgeons. They're like, don't mess with me. I can rip a phone book in half. Alright. So this is measuring the size. Two different ways. Our intensity. Right, we've got another guy. We've got the Mercalli scale. The Mercalli intensity scale. This is more for insurance companies, right? Determining the effect of the earthquake. Buildings are leveled. People are screaming. This one you guys have to take a look at on your own. I'm not going to write it on the board. But it does go through a level, right, Roman numerals would go from 1 to 12, 1 being not felt, 12 being complete destruction. All right, damage total. What was used as the standard to put together this Mercalli intensity scale? What state? Yeah, California is the standard. Really important to remember this doesn't measure energy, right? It's just measuring effect. Just effect. Primary hazards for earthquakes. We're sitting here happy as a clam, and all of a sudden, boom, 7.5 goes off. What are we hitting? That should be an S. First of all, if a 7.5 earthquake hits, get under your desk. Okay, I'm just gonna, and hold on. But, in terms of primary hazards, 3 things happen. First thing that's going to happen right up at the stadium, we're going to have our surface fault rupture. Alright, this is the point where the ground actually moves. Be very interesting to see. The next thing we'll find is tectonic deformation. Put it into perspective, right? Mountains go up. Valley will go down. Tectonic deformation. If we were by Alaska and we had a megathrust earthquake, magnitude 9.2, we could pop up as much as 8 meters. Interesting things will happen. And then we have our ground shaking. Everything, including video camera, all these rocks. In fact, if I go under this desk, these rocks will probably fall on me. That would be very painful. But these are our primary hazards that's happening as the earthquake goes off. Then we have our secondary hazards, which our friends down in the valley are going to experience, which we'll probably experience if we make it through an earthquake. All right, we have our secondary hazards. What's one we're all expecting?
Liquefaction.
Liquefaction. Liquefaction. The soil behaves like water. This is because we're changing the pore pressure. Between grains. If you have no idea what I'm talking about, to study for the exam, go out to the Great Salt Lake this weekend, stick your feet right at the shore, and go like this. Right? You will be shaking the sand, changing the pore pressure, and you're going to sink. And then you're going to slop your feet back out. It's going to sound weird. But that is liquefaction. Next thing. Landslides. anti-gravity. Weaver State, built on a landslide. If you don't believe me, you can see the fault scarp. It's right there outside. Walk out that door, look up the cliff where you see the rocky face up there. That's the head scarp for the landslide. Check out the UGS interactive map. You'll see that we stand on QMS3. That stands for a major landslide. So we will definitely expect one here at Weaver State. You also, Davis campus and you guys, I have your numbers. I don't really have your numbers, but I'm calling you. When the earthquake goes off, we're going to go unbury me, because there's going to be a landslide where I live too. All right, next thing we're going to have is fires. Right, we're going to cut gas. We're going to cut electrical, which those two things usually start fires when they're introduced to each other. And then we cut water, so we can't put it out. So this is a major hazard. We'll probably have our CJ, right, sloshing back and forth. Particularly Great Salt Lake. If you have a pool in your backyard, you'll probably see that as well. Sloshing back and forth. And then our final one, right, is a tsunami. Not so much of a hazard for Utah, but definitely along the coast. And why is a tsunami formed?
Land displacement.
Water displacement,
Water displacement.
right?
Because the land is displaced.
Yeah. What's the tallest tsunami ever recorded?
South.
Washington State.
No, it was up in Alaska.
Alaska.
1,742 feet, higher than the Empire State Building, higher than the Sears Tower, higher than any of the buildings we've ever built. And it was caused by a landslide in a bay. All right, so some more definitions. An earthquake risk. When we're talking about an earthquake risk, this is a potential of a risk to cause harm. So we define as an earthquake risk.